All right, instantaneous rate of change is actually a little easier than the other rate of change, I think, but we'll see. So we said that the average rate of change was the average slope. We use the slope formula for the line. Instantaneous rate of change is the slope right at that place. And slope at a point, that's a derivative. All right, so let's get a derivating. That's not how you say that word. So we have f prime of a is the instantaneous rate of change of f. All right, so that's our definition, instantaneous rate of change. And the thing here is that usually we leave out that word. So if we want average rate of change, we have to say the word average. If we just say rate of change, we mean instantaneous rate of change. Okay? So instantaneous just means derivative, and usually we drop the instantaneous part. Let's do example 2. All right. For f of x equals x squared plus x looks a little familiar to video 1, if you remember video 1. Find the rate of change. And remember, I didn't write instantaneous or average, which means instantaneous. If we don't specify, it's instantaneous. So find the rate of change of f at x equals 1. So again, all that is the derivative at that spot. Okay? So let's find the derivative. F prime of x is equal to, use the power rule, derivative of x squared is 2x, and the derivative of x is 1. And now we just have to plug in 1. So we will go over here and say f prime of 1 is equal to 2 times 1 plus 1, which is just 3. So in the other one, we found that the average rate of change over a long interval was 4. Over a short interval, we found that the average rate of change was 3.1. Instantaneous over an infinitesimally small interval, the rate of change is 3. Okay, so as we break down the average interval, it gets closer to that instantaneous rate of change. It gets closer to that derivative, which is how slopes work. All right, so that's that one. Next example, we go to the next page. And, whoa, there's a graph here. How fortunate for us that there's already this beautiful graph. So here we have this function, and we have a tangent line. This blue line is the tangent line at this point right here. Okay, so what we're going to do is, this is example number 3, unless I'm counting off, which is completely possible. Consider f of t. So that's the white one, which is the population in millions of the US T years after 1800. And we're going to ask a couple things about this. So, for example, right here we have the point 70, 40 right here. That means when t is 70, so that's in 1870, 70 years after 1800. In 1870, f of t is 40. So in 1870, there were 40 million people in the United States. A couple fewer people than there are now. All right. We have some questions. We have to, for space reasons, we have to write the questions on the next page, but we'll always be bouncing back. All right. So part A is, what is the average growth, or what was the average growth rate from 1840 to 1870? And remember that t is the years after 1800. So, right, this is t is equal to 40. This is t is equal to 70, and we want to find the average growth rate, the average slope. All right, from 40 to 70. We're going to look at the point at 40 and the point at 70. All right, and remember, we're looking at the function. So even though there's this other point over here, we're looking at the function. So those are the 2 points we're looking at. We're looking at the average slope, the average growth rate. That's going to be like this green line. Remember, the green line, the secant line, that's for averages, and the blue line is for instantaneous. That's the derivative. So at 70, we're at 40. And at 40, we're at 17. So we're just going to find the average rate of change using our average rate of change formula, right? Which says it's going to be f of the second minus f of the first divided by the second minus the first. What's the change in population? What's the change in years? And divide them out. All right. So what is the function value at 70? That's the first blank. Function value at 70 is 40 million people. So just 40. Minus, what is the function value when t is equal to 40? Well, let's look. When t is equal to 40, the function value is 17, like 17 million people. 70 minus 40 is just 30. And we can simplify this out. It'll be 23 over 30, which is approximately 0.76 repeating. All right, we have 0.76 repeating million people per year. That's our average growth rate. Let's rewrite that, right? 0.76 million people, that's kind of weird. So what we're going to say is the growth rate is, well, 0.76 million is 766,000. You could leave it there if you wanted to, or you could keep on going. 667 people per year. That's the average growth rate in this time. How many more people did we get? We got 23 million people. And how long did it take? 30 years. So that's the average growth rate. That's about how many people the population was growing by every year. All right. And checking the time because I have to go to class soon. Don't want to miss class. You know, it's a little easier to miss class as a student than as a professor, I think. Anyway, let's do part B. Part B is how fast was the population growing? We found the average growth rate. Now, once the instantaneous growth rate in 1840. So that's going to be the derivative of the function, the slope of the function. All right. So you go back. Derivative in 1840, that's when t is equal to 40. We have this nice tangent line already given to us. We just have to find the slope of that tangent line, which the slope of the tangent line here is kind of hard to find. But remember the slope of this blue line, we have a point here and we have a point here. So just use the slope formula on these 2 points. Okay, that'll give us the slope of the tangent line, which is the derivative, which is the instantaneous rate of change. All right. So that's what we're going to do. We're just going to find that slope function, which was rise over run. So 42 minus 17, that's the change in y values. 42 minus 17. Over the change in x values, which is 90 minus 40. And I know instantaneous rate of change is a derivative, but we don't have a function to take the derivative of, so we have to find the slope of the tangent line with this method instead. That's going to be 25 over 50. Oh, I like that number. That's 1/2. So the population was growing by 1/2 million per year, which is 500,000 people per year. So in 1840, it was growing by 500,000 per year, but the average growth rate was actually higher. And this makes sense because this blue line is the instantaneous growth rate in 1840. But the green line, that's the average growth. So notice the average growth is greater than the instantaneous growth because the green line is steeper. The green line has a bigger slope. Okay, so it should make sense that way. All right, last question for this video. Going to be part C, which says, was the population growing? Oh my word. I'm on the wrong tool here. Part C, was the population growing faster in 1810 or 1880? And again, remember, 1810, that's t is equal to 10. In 1880, that's t equals 80. So is the population growing faster? Okay. Is the slope bigger? At which one? Let's check. Let's look at the slope at 10 and at 80 and see which one's bigger. So the slope at 10, 10's right here. If we looked at the tangent line at 10, we'd get something that looked a little bit like this. If we looked at the tangent line at 90, we get something that looks a little bit like this. So is the green line or the yellow line steeper? Is the slope of the green or the slope of the yellow steeper? That tells us which one is growing faster. And yep, the slope of the yellow line is much steeper. The population is growing faster in 1890, which makes sense. A lot of population growth is exponential. So later on, the growth is more. I keep on getting stuck on this little line thing. That's our answer right there. All right, so that's it. Good luck on these problems. And then we'll move on to velocity and acceleration in the next video. And then approximate rate of change for applications in the last one. That's a good one. You're going to look forward to that one. All right.